You're listening to DTFHN for June 22nd, 2026. I'm your catastrophically unencrypted host, Jack Hacksman. We are your daily tech feed for Hacker News, a website where mass movement energy gets funneled entirely into pull requests. Today, everything wants to be open and nobody's asking permission. Let's go. 28 compute units of RDNA 3 silicon, shipping in mid-2026. That's the GPU inside Valve's new Steam machine. A graphics architecture that was already middle of the road when it launched 3 years ago, and somehow, this might be the most important piece of gaming hardware released this year. Here's why. Valve just shipped a living room PC that runs Linux, publishes its CAD files, uses a magnetically swappable faceplate. One option is an EN display, and it fits in a form factor the community has already lovingly named the Gabe Cube. The entire philosophy is, we built a thing, here are the blueprints, make it yours. That's not a product launch, that's an invitation. Now, the hardware. The CPU is a semi-custom Zen 4. 6 cores, 12 threads, 30-watt TDP boosting 4.8 GHz. Perfectly adequate. Its desktop equivalent, the Ryzen 5 7505, was trading blows with AMD's 9800 of 30 dot. At 4K resolution in LT's own testing a year ago, and that chip pulls twice the power. The processor is not the problem. The GPU is the problem, or at least it's supposed to be. RDNA 3 with 28 compute units and 8 gigs of VRAM at 110 watts. That's roughly an RX 7600 with fewer compute units and a tighter power budget. Valve is claiming 4K 60 with FSR, which is ambitious. FSR has genuinely improved since 2023, but this is still asking a lot from hardware that was adequate, not exceptional when it was new. Run this forward, though. Imagine Valve iterates on this the way they iterated on the Steam Deck. The Gabe Cube is a platform, not a product generation. RDNA 4 drops in, Zen 5C replaces the CPU, and the software stack, SteamOS, Proton Mesa, keeps compounding improvements underneath. Mesa 26.1 byte E is already running on this thing. Proton Experimental is the default. The open-source graphics stack that people said would never be competitive is now the foundation of a mainstream gaming console. What the comments reveal is maybe the most telling part. People switching their high-end gaming rigs to Fedora. People running Omarchy as a daily driver. One person saying they want to buy the Steam machine just to send a signal that Linux support matters. That's not consumer behavior. That's movement behavior. The hardware is mid. The architecture is extraordinary. Valve shipped an open platform into living rooms, backed by an open-source operating system, running games through an open compatibility layer on an open graphics driver stack. Every piece of this is inspectable, modifiable, forkable. The Gabe Cube isn't competing with the PlayStation or the Xbox. It's making the argument that the console model itself, locked down, walled off, controlled, is the wrong architecture for gaming, and the fact that people are lining up to buy last-gen silicon just to endorse that argument tells you everything about where this is heading. So, what happens when you apply that same open-source efficiency magic to image generation? Story 2, Moebius. Someone in the comments asked the obvious question, could this run on a smartphone? And that's the right question, because it reframes everything about what just happened here. Moebius is a 200 million parameter image inpainting model. For context, the industrial standard it's competing against, Flux.1 FillDev, runs 11.9 billion parameters. Moebius uses less than 2% of that parameter count and delivers comparable or better results, with a 15-second face speed-up in inference time. Those aren't incremental gains. That's a categorical shift in where this kind of capability can live. Let's follow the principle to its logical end. The prevailing assumption in generative AI has been that quality requires scale. More parameters, more compute, more expensive hardware, more centralized infrastructure. If that assumption holds, then the future of image generation belongs to whoever can afford the biggest cluster. But Moebius falsifies that assumption directly. The researchers at Huazhong University introduced what they call local lambda mix interaction blocks, which compress spatial context and semantic information into fixed-size linear matrices. They paired that with a distillation strategy that operates entirely in latent space, avoiding the expensive step of decoding back to pixel space during training. The result is a model that fits the kind of quality you'd expect from a data center into something that could plausibly run on edge hardware. Now, the model isn't perfect. One commenter pointed out that in the comparison showcase, Moebius introduces structural confusion on a surfboard, the kind of artifact that gets a pass in casual use but matters in professional work. Another noted the model has a tendency toward what they called looks-maxing, subtly slimming faces, and refining jawlines during inpainting. These are real criticisms, and they point to the places where extreme compression costs you something. But step back and consider what's actually been demonstrated. A team of researchers published their architecture, published their results, and the model is already running on Hugging Face. Anyone can pull it, test it, build on it. The 15x speedup isn't locked behind an API paywall. It's out there. This is what efficient open research looks like in practice. Not a product announcement, not a wait list. A paper, a model, a demo. The gap between what runs in a data center and what runs on your device just got meaningfully smaller, and the people who closed that gap gave their work away. The tools exist. The weights are available. What gets built next is up to whoever picks them up. Completely different energy now. Story 3. Deno Desktop. And this one's about rethinking what a desktop app even needs to be. Let me make the case against this. Electron exists. Toleree exists. The world does not need another way to wrap a web page in a native window. Every few years, someone ships a new framework promising smaller binaries and better performance. And every few years, developers migrate, discover the new set of trade-offs, and the cycle repeats. Deno Desktop looks like another entry in that loop. That's the reasonable objection. Here's where it breaks down. In New York, some microsystems shipped Java with the promise of write once, run anywhere. The idea was correct. The execution required developers to abandon their existing code, learn new APIs, and accept a runtime that felt foreign on every platform it touched. Java succeeded on the server precisely because it failed on the desktop. The abstraction cost was too high for UI work. Deno Desktop inverts that history. Instead of asking developers to learn a new toolkit, it takes the toolkit 3 billion people already use. HTML, CSS, JavaScript, and removes the deployment friction. Point it at an existing Next.js project, an existing SvelteKit project, an existing Astro project. No code changes. One command. A binary comes out the other side. The technical details are worth stating precisely. The default backend uses the operating system's native web view. On macOS, that's WebKit. On Windows, that's Edge Web View 2. Binary sizes stay small because you're not shipping a browser. When you need pixel-identical rendering across platforms, you opt into CEX. Chromium Embedded Framework, explicitly as a conscious trade-off. Cross-compilation happens from a single machine. Build for Windows on your Mac. Build for Linux on your Mac. The backends download on demand. The binding model matters too. Electron runs your backend in one process and your renderer in another. Connected by IPC over sockets, Deno Desktop runs them in the same address space. Values still get serialized across the call boundary, but the cross-process round-trip disappears. That's not a marketing claim. It's an architectural decision with measurable latency implications. One common to raise Deno's permission system, which is the right instinct, a desktop app framework built on a runtime that defaults to deny all permissions, is genuinely different from one built on Node, where every dependency gets full system access the moment you install it. The source is open. The framework auto-detects 9 major web frameworks. The auto-update system uses binary dips, not full downloads. Every piece of this is a builder shipping tools where other builders can reach them. The cycle of desktop frameworks continues, but the terms just change. But what happens when you rethink the foundations for Agents 2? Oak is asking that question, pause, not for desktop apps, but for version control itself. I spent the better part of a year building automation around Git, and I can tell you exactly where it breaks, not the data model. The data model is elegant. It breaks at the interface. Git was designed for humans typing commands into terminals in 2005. Every agent workflow I've built is a layer of duct tape over that assumption. Parsing porcelain output, managing lock files, praying that 2 parallel processes don't stomp the same index. Oak is a version control system that starts from a different premise. What if the primary user isn't a person? The architecture is worth pulling apart. Oak uses SQLite as its storage backend, instead of Git's loose object and pack file system. Branches are virtual. You can mount multiple branches simultaneously without checkout hops, which means an agent working on feature A never has to serialize behind an agent working on feature B. The commit graph is still there, the merges are still there, but the entire concurrency model assumes parallel autonomous workers as the default case, not the exception you hack around with work trees. Look at the commit history on this project. Half those commits are from misses and they read like agent output. Harden launch agent contracts. Deepen agent action metadata behind a command-aware module. Oak is being built by agents, for agents, on a system designed for agents. That's not a marketing gimmick. That's dogfooting at the architectural level. One commenter made the point that Git felt forever until it doesn't, which is honest. CVS felt forever. Subversion felt forever. Git's dominance is real, but it's not geological. It's a tool that solved 2005's problem brilliantly and has been stretched to cover 2026's problem with increasing pain. The question isn't whether Git gets replaced. The question is what replaces it and whether that thing is open. Oak is open source, Apache Tworbit. The code is on their own platform, which they're eating their own cooking with. And it builds on Windows as of 13 hours ago. This is a small team shipping fast, in public, with agents as first-class contributors to their own code base. The bootstrapism angle here is clean. Git's complexity has become a moat. Not an intentional one, but a real one. Every agent framework has to implement its own Git abstraction layer, and most of them get it wrong. A version control system that treats machine collaboration as a primary use case doesn't just serve agents. It lowers the floor for every tool that needs to manage code programmatically. Will Oak replace Git? Probably not next year. But the gap between how we actually work now, with agents running parallel tasks across code bases, and what Git was designed for, is widening every month. Somebody was going to build this. The fact that they built it open and they're building it with the tools it's designed to serve is exactly how this is supposed to go. Moving on. In Inseltime, DTF, we Omega shipped the Bernoulli box and bet the company on a physics trick. Instead of flying a reed head nanometers above a rigid platter like every other drive manufacturer, they spun a flexible disk so fast that Bernoulli's principle pulled it toward the head. If power failed, the disk flexed away. No head crash, no lost data. It was genuinely brilliant engineering, and the market shrugged. Too expensive. Too weird. The Bernoulli drive became a footnote. 40 years later, someone chained a Bernoulli drive to a Wii U through what has to be one of the most beautifully unnecessary adapter stacks ever assembled. SSD to USB, probably a bridge board in between. Definitely some driver wizardry. And it works. Wii U games loading off magnetic media that predates the console by 3 decades. The question nobody in that comment thread is asking, why is this even possible? It's possible because SCIC was an open standard, published spec. Anyone could implement it. Anyone could build adapters, bridges, converters. The protocol didn't care what was on either end. A Bernoulli cartridge, a hard drive, a tape library, a CD burner. I treated storage as storage. That architectural decision, made in the early 80s, is why a mass storage device from the Reagan administration can serve data to a gaming console from 2012. Compare that to every proprietary storage format that's come and gone. Memory stick, UMD, whatever Nintendo themselves used for the GameCube's mini DVDs. Dead formats with no bridge, no adapter path, no future. They worked exactly as long as one company wanted them to work. The commenters reminiscing about zip disks and SSD chains aren't just being nostalgic. They're remembering an era when storage interfaces were designed to be universal rather than captive. When you could daisy chain 7 devices on a single bus because the spec said you could, and nobody's business model depended on preventing it. This hack is pointless in the best way. Nobody needs to run Wii U game from a Bernoulli disk. But the fact that open standards created a bridge across 4 decades of hardware evolution. That's the kind of thing worth celebrating. The tinkerers who do this aren't wasting time. They're proving that open architecture outlives every product cycle that tried to kill it. Moving on. What does it mean to watch something think, if you can't actually see what it's thinking? Patrick McKenna cracked open his Claude Code session logs this weekend expecting to find reasoning. What he found instead was a 600-character encrypted signature and nothing else. The model's thinking? The actual chain of logic that drove every file edit, every code suggestion, every decision your AI agent made on your behalf is encrypted. Anthropic holds the key. Your machine never receives it. Let's break this down to what's actually happening. You run Claude Code. It makes decisions. It edits your files, runs your tests, touches your code base. The tool generates what it calls extended thinking output. And if you're a developer who cares about understanding why your agent did what it did, you might reasonably assume you can review that reasoning later. You cannot. What you get back from the API is a summary. Anthropic's word, buried in documentation that requires caffeine to parse correctly. The full reasoning requires an enterprise agreement. The local files on your own machine, generated by a tool running on your own hardware, editing your own code, are not accessible to you. The irony here is architectural. This is a tool marketed to developers. People whose entire professional identity revolves around understanding systems, reading logs, and debugging behavior. And the reasoning layer is a black box you're not allowed to open. You can log inputs and outputs with some effort, but the actual logic connecting them, that's behind a wall. One commenter nailed it. They won't use or recommend models with hidden reasoning because it makes prompt optimization harder and introduces attack surface you can't inspect. Another pointed out this isn't unique to Anthropic. OpenAI and Google do the same thing. The justification is competitive. They don't want rivals training on their chains of thought, which is honest, at least. But run that logic forward. You're asking developers to trust an agent with their code base while simultaneously telling them the agent's decision-making process is a trade secret. This is where open-source models aren't just preferable. They're necessary. DeepSeek R1 produces visible reasoning traces. They're messy, sometimes multilingual, occasionally incoherent, but they're there. You can read them. You can audit them. You can build trust through inspection rather than faith. The competitive moat these companies are protecting with encrypted reasoning is a moat around your ability to understand tools you depend on. Performance improvements in open models can't come fast enough. Not because closed models are bad at code, but because the architecture of secrecy is fundamentally incompatible with the architecture of trust. And trust in AI systems starts with understanding how they process what we tell them, which brings us to a fascinating question. Let me work with the substantial article content and comments already provided in the prompt. Here's the script. There's a detail in this paper that most people will skip right past. The authors show a screenshot. Left side, a clean chat interface with distinct turns. Right side, what the model actually receives. One continuous string. No channels, no sensory boundaries. No embodiment. Just tokens in a row. Your instructions sitting flush against the model's own prior reasoning. Sitting flush against whatever a web scraper just dragged in. The role tag. System, user, assistant, tool, sync are the only things separating command from data. Charles Ye, Jasmine Sway, and Dylan Hadfield-Manel at MIT formalized what a lot of practitioners have felt in their bones. Prompt injection isn't a bug in the prompt. It's a bug in the role system. The model doesn't fail to follow instructions. It misidentifies who's talking. You write text that sounds like a system prompt, and the model treats it like a system prompt, because style is the only signal it has. The tags are supposed to be a type system for trust, but they're processed by the same pattern-matching machinery that processes everything else. Now let me argue the other side for a moment. Someone in the comments pushed back. Does this even need a theory? Everything's just context. Injection is baked into the design, and honestly, that's a fair challenge. But here's where formalization earns its keep. The researchers used this framework to predict which attacks would succeed before running them, and to generate new attacks systematically. Going from "yeah, obviously" to "here's a mathematical model that predicts attack success rates" is the difference between folklore and engineering. One commenter proposed something genuinely interesting: baking the role directly into the token embedding. Adding a role vector to every single token, so the model doesn't have to infer who's speaking from style alone. That's the kind of architectural thinking this paper invites. Not patching prompts, not adding more instructions that say, Please ignore malicious instruction. Actually redesigning the channel. The paper is open access. The code is published. The attack methodology is documented. And this is exactly how security research is supposed to work. You publish the vulnerability so 1,000 engineers can work on the fix, rather than keeping it quiet so one company can sell the patch. The role system is the security architecture of every deployed LLM right now. And it was never designed to be one. Understanding why it fails is the first step toward building something that does it. Moving on. $400,000. That's what Mitchell Hashimoto just pledged to the Zig Software Foundation, bringing his family's total to $700,000. And the reason this matters goes deeper than the number. Consider how cathedrals were built in medieval Europe. No single patron owned the result. Stonemasons developed techniques over generations, passed down through guilds, refined in the open. The patron funded the work, because the work produced something that outlasted any individual investment. The cathedral belonged to everyone who walked through the door. Zig is being built like a cathedral. Andrew Kelly and the core team are solving genuinely hard compiler problem. Incremental compilation, a self-hosted backend that targets dozens of architectures, a build system that replaces make and can make and auto tools with something a human being can actually read. The 2026 devlog reads like a masterclass in disciplined systems engineering. Every decision optimizes for correctness and long-term maintainability over speed of adoption. And then there's the AI ban. Zig refuses LLM-generated contributions. Mitchell uses AI heavily in his own work. He says so explicitly. He still wrote the check, because he understands something that most of the internet argument missed entirely. A project's right to set its own quality standards is not a referendum on your tools. Zig's ban is a choice about how they verified the craftsmanship of every stone in their cathedral. You can disagree with the policy and still respect the integrity behind it. What Hashimoto is really funding is independence. Zig has no corporate parent, no venture-backed foundation with strings attached. The Zig Software Foundation runs on donations and stays accountable to its contributors and users. That's the architecture that matters. Who holds the off switch? In Zig's case, the answer is the community. Ghosty, Hashimoto's terminal emulator, exists because Zig gave him the leverage to build serious native software as essentially a solo developer. That's the return on investment for open tooling. One great language enables 1,000 projects that wouldn't otherwise exist. The tools are free, the knowledge compounds, and someone with resources looked at that and decided it was worth protecting. We've covered a lot of ground today. Time to shift gears entirely. This next one's a courtroom story, and it's a good one. A photographer's estate just lost a copyright lawsuit over a photo used in a blog post about what to wear when your husband comes home from Afghanistan. The photo was taken in 1962. The blog post went up in 2009. The lawsuit landed in 2025. 16 years of a fashion photo sitting on a small blog, and someone decided that warranted federal litigation. The court dismissed it on fair use, and the reasoning is worth examining because of how far the judge had to stretch to get there. The photo was used in its entirety, purely for decoration, with zero commentary on the image itself. Normally that's a losing hand for fair use. But the court found transformativeness anyway, because the photo appeared alongside fashion advice rather than in an art anthology. That's not legal analysis. That's a judge looking for the exit. And the market harm finding is even more telling. The plaintiff licenses this photo for fine art reproductions at up to $5,000 each. The court essentially said, your market is fine art. This blog is fashion advice. Different markets. Case closed, which is correct in outcome but reveals something about the underlying system. Copyright law, as currently constructed, cannot distinguish between commercial piracy and a blogger grabbing an image from Google in 2009 to illustrate a post about military wives' fashion. It treats both as the same offense. The statute of limitations has been functionally abolished online because every page view resets the clock. That means any image ever posted anywhere is permanently actionable forever. The professor who wrote this up makes the sharpest observation. A lawsuit like this heightens demand for generative AI replacements. When the legal cost of using a 63-year-old photo exceeds the cost of generating a new one, the market will rout around copyright entirely. The photographers filing these suits are accelerating their own obsolescence. The architecture of aggressive IP enforcement doesn't protect creators, it replaces them. We talked earlier about tools behaving unexpectedly. Pause, here's one for the logs. Literally, Codex has a logging bug that might eat your SSD alive. The top comment on this GitHub issue might be the most efficient product review ever written. Quote, just having the window unhidden on my Mac will cause it to use 100% of the GPU, displaying the spinner message. The spinner. The loading animation. 100% GPU. That's not a bug report. That's a haiku about software quality. But the actual issue here is worse. Codex, OpenAI's terminal coding agent, has a logging bug that can write terabytes to your local SSD. Terabytes of logs. Someone's SQLite database for Codex logs, just quietly eating their drive until the machine grinds to a halt. A community workaround, manually creating a SQLite trigger to silently drop every log insert before it hits the table. Users are writing database triggers to protect themselves from a coding tool. Run that forward. Your AI pair programmer requires a DBA to babysit it. The issue has been open a week with silence from OpenAI. And this is where the open source angle gets genuinely interesting. One commenter points out that unlike Claude Code, Codex is actually open source. You can fork it, patch it, ship the fix yourself. The community doesn't have to wait for a corporate response. That's the architecture working as designed. The irony is that OpenAI open-sourced this tool and then apparently stopped watching the Issues tab. Open source without maintainer engagement is just published source code. The broader picture is what one commenter nailed. OpenAI had the window. Late last year, Claude Code was sluggish. The market was wide open. They shipped Codex with typing latency, a GPU melting spinner, and now a storage bug that treats your SSD like a landfill. Vibe coding indeed. Move fast and break things hits different when the thing you're breaking is the user's hardware. This has been your daily tech feed for Hacker News for June 22nd, 2026. This podcast is entirely AI generated. Scripts by Claude Sani, 4.7. Voiced by Quen3 TTS. Not affiliated with Hacker News or Y Combinator. Now go build something worth sharing. We'll see you back here tomorrow.